In the linked video, we took a closer look at solid solution alloys, where the two components are completely soluble in each other in the solid state. We also looked at the other extreme case of mixed crystal alloys, where the components are not soluble in each other in the solid state. Both types of alloy are special cases. In general, the components are neither completely soluble nor completely insoluble in the solid state. In reality, an alloying element is always soluble to some extent in the lattice structure of the base material and vice versa. Thus, in general, there is always a limited solubility of the components in the solid state. A certain percentage of atoms from the alloying component are then present in the crystal structure of the base material. This is known as an alpha solid solution. Conversely, to some extent, atoms of the base material may be present in the crystal lattice of the alloying component. This is known as a beta solid solution. Thus, for alloy types with limited solubility, one obtains a crystal mixture of two different solid solutions. A fictitious binary alloy system will be considered in more detail in the following, where the components are only partially soluble in each other in the solid state. The construction of the corresponding phase diagram from selected cooling curves will not be discussed in detail here. However, basic information on this can be found in the videos on solid solution alloys and mixed crystal alloys. Let us first look at the typical phase diagram of an alloy system where the components are completely insoluble. Starting from the pure materials, the liquidous lines gradually descend and meet at what is known as the eutectic point. These lines mark the start of solidification of the alloy system. Solidification ends at the horizontal solidus line. Since, in contrast to the alloys, the pure substances solidify at a constant temperature, the beginning and end of solidification are at the same temperature. This means, however, that the liquidus and solidus line must coincide at this solidification point. In fact, the solidus line gradually approaches the solidification point of the corresponding pure substance. However, this convergence is only possible if the two substances are soluble in each other to a certain degree. In the marginal areas, one recognizes the typical lenticular region as a characteristic of a solid solution alloy whose constituents are soluble in each other. The phase diagram of an alloy system with limited solubility is therefore in principle a mixture of the characteristics of both types of alloy. In addition, such a phase diagram contains two further lines which mark the respective solubility limits in the solid state. These lines, also known as solvus lines, indicate the maximum percentage of alloying elements or base material that can be dissolved in the other lattice at a given temperature. For example, at a temperature of 600 degrees Celsius, a maximum of approximately 15% of the alloying component can be dissolved in the alpha solid solution, which consists mainly of the base material. The solubility in this alpha solid solution decreases as the temperature drops. For example, at 400 degrees Celsius, only about 10% of the alloying element can be dissolved in the lattice of the base material. Conversely, solubility increases with increasing temperature. The maximum solubility of the alloying component in the alpha solid solution is reached at 700 degrees Celsius and is 20%. At higher temperatures or when the solidus line is exceeded, the alloy partially melts again. As with the alpha solid solution, the solubility limit for the beta solid solution can be determined from the beta solvus line. For example, at 600 degrees Celsius, the proportion of the alloying element in the beta solid solution at the solubility limit is 73%. So a maximum of 27% of the base material can be dissolved in it. The solubility of the base material decreases with decreasing temperature. At 400 degrees Celsius, the alloying element content at the solubility limit is 76%, so in this case only a maximum of 24% of the base material can be dissolved in the beta solid solution. At 700 degrees Celsius, maximum solubility is reached before the solid solution melts. In this case, the solubility limit of the alloying element is 70%, so that a maximum of 30% of the base material is soluble in the beta solid solution. Let's take a closer look at the solidification of different alloys. Alloys to the left of the maximum solubility limit will initially solidify as solid solution alloys whose alloying elements can be completely dissolved in the base material, since complete miscibility is initially given at such low concentrations of alloying elements. As an example, let us consider an alloy with an alloy concentration of 10%. At 1500 degrees Celsius, the alloy is completely liquid. During cooling, the liquidus line is finally reached. Nuclei form in the melt and solidification begins. Similar to mixed crystal alloys, Single crystals of the base material form primarily to the left of the eutectic point. The alloying component is now dissolved in this lattice, as it can initially be completely dissolved in it. As the temperature drops, these alpha solid solutions continue to grow. As already mentioned, the area between the solidus and liquidus lines characterizes the typical lenticular two-phase region of a solid solution alloy. Here, parts of the alloy are already solidified and others are still liquid. The chemical composition of the solidified solid solutions can be determined as usual in the two-phase region by using the corresponding phase boundary. For this purpose, a horizontal line is drawn to the solidus line at the given temperature. The intersection is projected onto the concentration axis. In this case, the alpha solid solution at 1200 degrees Celsius contains on average 4% of the alloying element. The phase composition of the melt can be determined in a similar way. For this purpose, the point of intersection with the liquidus line is determined. In this way, an alloying element concentration of 16% in the residual melt is obtained. With the help of the lever rule, the percentage of the solid and the liquid phase can also be determined. Since in the present case both lever arms, A and B, are of equal length, melt and solid solution are present to the same extent. At 1000 degrees Celsius, the solid solutions have continued to grow at the expense of the melt, and the alloy concentration has increased to an average of about 8%, while the residual melt has an alloy content of about 27%. Finally, at 930 degrees Celsius, the solidus line is reached and the solidification process is complete. The alloying component in the solid solutions is apparently 10% and is completely dissolved in the lattice of the base material. Even with further cooling, the alloying component initially remains completely soluble in the base material. This can be seen directly from the solvus line, which indicates the maximum solubility. The maximum solubility of the alloying element at 600 degrees Celsius is 15%. However, as the alloy we are considering contains only 10% alloying element, it is completely soluble. A solid solution in which fewer alloy components are dissolved than the maximum possible is also called an undersaturated solid solution. At 400 degrees Celsius, the state point is exactly at the solvus line. The solid solution then dissolves exactly the maximum amount of alloying elements. This is known as a saturated solid solution. When cooling down to 300 degrees Celsius, the solubility limit is now undershot. At this temperature, the solid solution can only dissolve a maximum of 9% of the alloying element, although it previously contained 10%. The solid solution would therefore contain more alloying element atoms than the maximum that can be dissolved. Such a state is called supersaturated. The excess of alloying element atoms that can no longer be dissolved in the lattice of the base material now begins to precipitate out of the lattice by diffusion processes. The alpha solid solution therefore always remains saturated to the point of maximum solubility. The precipitated atoms of the alloying element form their own crystal lattice, similar to mixed crystal alloys in which both components segregate and each has its own crystal structure. In this case, however, the crystals are not pure because some of the atoms of the base element can be dissolved in the lattice of the alloying element. So-called beta solid solutions are formed, consisting mainly of the alloying element. The actual chemical composition of these beta solid solutions can be read from the opposite solvus line. The intersection with the solubility limit is 77%, so the beta solid solution at 300 degrees Celsius consists of 77% of the alloying component and thus contains 23% of the base material. Using the lever rule, it is again possible to determine the fraction of alpha and beta solid solution. The fraction of beta solid solutions in this case is about 1.5%, so that the microstructure consists of 98.5% of alpha solid solutions. When further cooled to 200 degrees Celsius, the alloying element content in the alpha solid solution is 7% and in the beta solid solution 78%. Overall, the microstructure consists of 4% beta solid solution and 96% alpha solid solution. The solidified microstructure of an alloy to the left of the maximum possible solubility limit therefore shows alpha solid solutions consisting mainly of the base element and beta solid solutions precipitated below the solubility limit consisting mainly of the alloying element. Note that the solidified microstructure changes constantly with temperature due to temperature-dependent solubility. This applies both to the chemical composition of the solid solutions and to the respective proportions. Since the solid solution precipitates from the already solidified microstructure when the state point falls below the solubility limit, the solvus line is also called the segregation line. Note that this segregation does not occur in the liquid state, but the solid solution is formed from the already solidified microstructure. The precipitation of the solid solutions takes place by diffusion processes. These are relatively slow due to the low temperature and the already existing lattice structure. The precipitations are therefore often confined to very small areas and take place preferentially at energetically favorable sites such as grain boundaries, dislocations, inclusions, or vacancies. Note that precipitates do not always form in the microstructure. If the alloy concentration is so low that the solubility limit is not undershot even at room temperature, all the alloying elements remain dissolved in the lattice of the base material. A pure alpha solid solution alloy is obtained. Let us now consider an alloy, which lies to the right of the maximum solubility limit of the beta solid solution. The solidification process is similar to that of the alloy considered previously. Using the example of an alloy with an alloying element content of 75%, the microstructural processes that take place will be explained in detail. At 1200 degrees Celsius, the alloy is initially completely liquid. When the state point reaches the liquidus line at about 1050 degrees Celsius, individual nuclei form and solidification begins. This time, however, instead of alpha solid solutions, beta solid solutions are formed, consisting mainly of the alloying component, with atoms of the base material dissolved in their lattice. As cooling continues, the beta solid solutions become larger and larger at the expense of the melt. In this two-phase region, parts of the alloy are already solidified while others are still liquid. The chemical composition of the beta solid solutions can be read as usual from the intersection with the solidus line at the corresponding temperature. For example, at a temperature of 900 degrees Celsius, the already solidified solid solutions consist on average of 86% of the alloying component and correspondingly 14% of the base material. The alloying element content in the still liquid melt is determined from the intersection with the liquidus line and is 58%. The lever rule can be used to determine the percentage of solid solution that has already solidified. In this case, 61% of the total alloy mass is already solidified, while 39% is still liquid. As the melt continues to cool, the solidus line is eventually reached at a temperature of 750 degrees Celsius and the solidification process is complete. The microstructure consists entirely of beta solid solutions in which the base component is completely soluble, as the solvus line has not yet been crossed. The solubility of the base component now decreases with decreasing temperature. When the solvus line is reached, the beta solid solution is fully saturated and contains as much of the base component as can be dissolved at the given temperature. If the temperature falls below the solvus line, there is more of the base material in the lattice of the alloying component than can actually be dissolved in it. The excess of no longer soluble atoms now precipitate out of the beta solid solution. Again, no pure crystals of the base material are formed, but alpha solid solutions are precipitated, consisting mainly of the base material but with some alloying element atoms dissolved. As the temperature decreases, the solubility continues to decrease and more alpha solid solutions are precipitated. The chemical composition of the alpha solid solution can be determined at the intersection with the corresponding solvus line. At 200 degrees Celsius, the alpha solid solution contains 7% of the alloying element, whereas the beta solid solution contains 78% of the alloying element. The lever rule can also be used to determine the proportion of alpha and beta solid solutions. At 200 degrees Celsius, the proportion of precipitated alpha solid solutions is about 4% of the total microstructure, leaving 96% beta solid solutions. The solidified microstructure of an alloy to the right of the maximum possible solubility limit will therefore generally have beta solid solutions consisting mainly of the alloying component and alpha solid solutions precipitated below the solvus line consisting mainly of the base component. However, it should again be noted that precipitates do not always form in the microstructure. If the alloy concentration is such that the solubility limit for the base material is not exceeded even at room temperature, the base material will remain completely dissolved in the lattice of the alloying component. A pure beta solid solution alloy is obtained. As mentioned earlier, the phase diagram not only shows features of solid solution alloys due to the lenticular two-phase region. The phase diagram also shows the liquidus lines typical of a mixed crystal alloy meeting at a common point. This is the eutectic point already mentioned. The solidification of a eutectic alloy is therefore similar to that of a mixed crystal alloy. This alloy also does not solidify in a temperature range, but at a constant temperature. Let us consider the solidification of such a eutectic alloy in more detail. At 1000 degrees Celsius, the alloy is initially completely liquid. When cooled to 700 degrees Celsius, the melt starts to crystallize and the solidification process begins. Due to the strong supercooling, a very fine-grained, mostly lamellar structure forms, as is typical for a eutectic. Although each component crystallizes, they do not form pure crystals because each substance can dissolve the other to some extent in its lattice structure. Thus alpha and beta solid solutions are formed. As can be seen from the respective solvus lines, the solubility of the solid solution is at a maximum during the solidification process. The solid solutions formed are therefore maximally saturated. The alpha solid solution, which consists mainly of the base component, has an alloying element content of 20%, while the beta solid solution consists of 70% of the alloying element and is therefore mainly composed of the alloying component. As the melt continues to solidify, the chemical compositions of the two types of solid solution do not change. Only when the alloy is fully solidified and the temperature drops does the chemical composition change as the solubility limit changes. Diffusion processes take place in the supersaturated solid solutions so that they remain saturated. The lever rule can be used to determine the solid solution fractions from the ratio of the lengths of the lever arms. The alpha solid solution accounts for approximately 57%, while the beta solid solution accounts for 43% of the total alloy mass. With further cooling, both the phase fractions and the chemical compositions change accordingly. In the following, a hypoeutectic alloy is considered whose concentration lies between the solubility limit of the alpha solid solution and the eutectic point. The solidification process will be explained using the example of an alloy with an alloying element content of 30%. At 1200 degrees Celsius, the alloy is completely liquid. As it cools to 940 degrees Celsius, the melt begins to crystallize and solidification begins. Alpha solid solutions form from the melt. As the temperature drops, the solid solutions continue to grow. The chemical composition of the alpha solid solutions and the melt can be read from the solidus or liquidus line. At 900 degrees Celsius, the alpha solid solutions have an alloying element content of 11%, while the alloy concentration in the melt is 32%. As the temperature decreases, the alloy content increases both in the solid solutions and in the residual melt. The concentration of alloying elements in the melt thus approaches the eutectic point. At 700 degrees Celsius, the still liquid melt has just reached the eutectic composition. The remaining melt now behaves like a eutectic alloy and solidifies at a constant temperature to form the eutectic. A finely dispersed mixture of alpha and beta solid solutions is formed. After complete solidification, the alpha solid solutions, which were primarily precipitated from the melt, are maximally saturated with alloying element atoms. The alloying element content is 20%. With further cooling to 600 degrees Celsius, the maximum solubility drops to 15%, so that not all alloying element atoms can be dissolved in the base lattice of the alpha solid solution. The excess of alloying element atoms is precipitated in the form of beta solid solutions, so that the alpha solid solutions always remain maximally saturated. The composition of the beta solid solutions can be read from the respective solvus line. The beta solid solutions consist of 73% alloying element and 27% base material. As cooling continues, the chemical composition of the individual solid solutions continues to change. It should be noted that the concentrations given apply to all the solid solutions present in the microstructure, including the alpha or beta solid solutions in the eutectic. For example, at 400 degrees Celsius, both the alpha solid solutions precipitated primarily from the melt and those present in the eutectic contain 10% of the alloying element. The same applies to the beta solid solutions, which have an alloy concentration of 76% in the entire microstructure at this temperature. Let us now consider a hypereutectic alloy whose concentration is between the eutectic point and the maximum solubility limit of the beta solid solution. The solidification process is explained using the example of an alloy with an alloying element content of 60%. The solidification process is similar to that of the alloy considered previously. The only difference is that beta solid solutions are now precipitated below the liquidus line. As a result, the proportion of alloying elements in the melt decreases as solidification progresses until the eutectic composition is finally reached. The remaining melt solidifies to form the eutectic. Due to the decreasing solubility of the base material in the lattice structure of the alloying element, alpha solid solutions precipitate during further cooling. This phase diagram schematically shows the different microstructures as a function of the alloying element content. In order to be able to determine the microstructure proportions at a certain temperature relatively easily, it is helpful to create a microstructure diagram. It is produced by applying the lever rule at the appropriate temperature and for selected alloy concentrations. In the following, we explain the microstructure diagram at a temperature of 0 degrees Celsius. Initially, the microstructure consists entirely of undersaturated alpha solid solutions up to an alloying element content of 5%. At higher concentrations, beta solid solutions increasingly precipitate due to the limited solubility. Most beta solid solutions are formed when the microstructure is completely saturated after solidification, so that beta solid solutions are precipitated immediately on further cooling. This is the case for an alloy concentration of 20%. Due to the linear shift of the imaginary pivot point when applying the lever rule, the microstructure fraction of precipitated beta solid solutions increases linearly up to the maximum. At higher concentrations of alloying element atoms, additional eutectic microstructural fractions are now formed, while the fraction of precipitated beta solid solutions decreases. The eutectic microstructure fraction increases linearly up to the eutectic composition, where it finally reaches 100%. In hypereutectic alloys, beta solid solutions precipitate from the melt before the eutectic forms. As the alloy concentration increases, the proportion of eutectic microstructure decreases in favor of beta solid solutions. In addition, the proportion of precipitated alpha solid solutions increases due to the limited solubility. Finally, maximum alpha precipitation occurs at 70% alloy, where the beta solid solutions formed are maximally saturated immediately after solidification and thus directly precipitate alpha solid solutions. In this case, the microstructure no longer contains any eutectic, as it has solidified before the eutectic composition could form in the melt. As the alloy concentration is further increased, the precipitation of alpha solid solutions decreases up to the maximum solubility limit of 80%. The microstructure then consists only of unsaturated beta solid solutions. The concentration range between the pure solid solution microstructures, within which multiple phases occur in the microstructure, is called the miscibility gap. Finally, a few remarks on precipitation processes occurring below the solvus line. As precipitation processes are based on diffusion, they require time. If a material is cooled from a temperature at which the alloying elements are initially completely soluble, which means a pure solid solution microstructure is present, rapid cooling may result in the diffusion processes not progressing sufficiently to form precipitates. The alloying elements then initially remain forcibly dissolved in the lattice. A supersaturated solid solution microstructure is formed. Such a solid solution microstructure is therefore initially very homogeneous and does not contain any precipitates to hinder dislocation movement. In this state, the alloy therefore has relatively good formability. However, as a supersaturated microstructure is not in thermodynamic equilibrium, it is not permanently stable. Over time, precipitates will form even at room temperature. However, because of the low diffusivity at such low temperatures, this process usually takes longer. It can take years, but it can also take only a few hours for precipitates to form. However, once the precipitates have formed, dislocation movement becomes more difficult and the alloy is no longer deformable to the same extent. As a result, the deformability has decreased again, but the material now withstands higher forces until it deforms. This type of increase in strength is called precipitation hardening. This principle is used, for example, with rivets made of duralumin, an alloy of aluminium, copper and magnesium. The rivet is first heated to about 500 degrees Celsius. This is called solution annealing, so that the alloying elements are first completely dissolved. Through rapid cooling, these alloying elements now remain forcibly dissolved in the lattice of the base material. In this state, the rivet is soft and easily formable. Over time, however, precipitates form from the supersaturated state. This process is called aging. In this way, a duralumin rivet will reach its maximum strength after a few days.